We're going to work through the solution for one of the more challenging combination circuits that we've got. And you see that I've put the givens and finds up here. Basically, for all of these problems, we're going to have to find the total resistance, the total current, all of the voltages, and all of the currents through each of the circuit components. The first step in this problem is to find the total resistance, and we have to look at the parts of the circuit that are interior, the simple connections within the larger circuit itself. And in this case, R1 and R2 are the most simple combination, and they're combined in parallel. So we'll work through the solution for the combination of 1 and 2 first. Make your substitutions. And we get 2 ohms for the combination of 1 and 2. You can redraw that as one circuit now, and that one circuit would be combined with R3 in series. R123 would therefore be R12 plus R3. Giving us 6 ohms for R123. That combination is then combined in parallel with R4. So R1, 2, 3, 4, we would have to use the parallel combination equation. Giving us 4 ohms. And finally, our total would be the combination of 1, 2, 3, 4, and 5, and R1, 2, 3, 4 is in series with R5, so we would add those values together. So the total resistance of this circuit is 12 ohms, which means 12 ohms resistance will determine the total current within this circuit. So if we want to find the total current, we have to use that total resistance along with the total voltage. Our total voltage of this circuit is 54 volts. Which gives us 4.5 amps of current through the entire circuit. The next part of the solution is a very important part, and it's where we're trying to apply the loop theorem and the junction theorem. We'll take a look at the junction theorem first. When we're looking at the junction theorem, we identify the various junctions within the equation, and we look at the current going into the junction and coming out of the junction. So for example, this first junction that we come to, we have the current that comes through resistor 5, and that goes into the junction, and coming out of that junction is the current through resistor 1, the current through resistor 2, and the current through resistor 4. So an equation that we can write for that is the total current going into that junction, which is I5, is equal to the current coming out of that junction, which would be I1 plus I2 plus I4. We can identify another junction right here where we have the current coming into that junction would be I1 and I2, and the current leaving that junction would be I3. So the equation would be I1 plus I2, which is going into that junction, is equal to I3, which is coming out of that junction. Another junction is right here. We have the current coming through resistor 3 and the current coming through resistor 4 combining together to give us the total current in this circuit. So I3 plus I4, which is the current going into that junction, is equal to I total, which is the current coming out of that junction. Now, another thing that you can look at is this total current for the circuit does go through resistor 5 before it gets to any junction. So what that tells us is that I total is equal to I5. Those are the equations that we would use for our junction theorem. Now we want to take a look at our equations from the loop theorem. To apply the loop theorem, we have to be able to trace the paths of conduction, and for this circuit there are several. So we can go from the battery through this path of conduction, and at this point where we get to the junction, we can choose several different ways to go to create a closed loop, a complete path of conduction. So if I look at the one that I've just traced, on that loop we rise a total of the voltage through the battery of 54 volts, and then we come down in voltage through each of those two resistors. So the total rise is equal to the total drop, which would be V5 plus V4. We can look at another path of conduction, again through resistor 5, and this time through resistor 2 and 3, and back around. And for that loop, again, the rise is the total voltage. Then we're coming down through resistor 5, resistor 2, and resistor 3. We've got a third path of conduction through resistor 5, through resistor 1, and all the way back to the battery. And these are independent paths, independent loops, so we can write our equation for this one, V5 plus V1 plus V3. If we compare the last two equations we wrote, we've got V5 plus V2 plus V3, and V5 plus V1 plus V3, and that total would each be the total voltage. So from that we can draw the conclusion that V1 would also be equal to V2, which makes sense if you look at the connection because those two are in parallel. Those two resistors are in parallel. This set of equations then becomes our puzzle pieces to solve the rest of the problem. And we already have our total current, and with this set of equations we can then take a look and try to find the one piece that will start us off with the solution. And what I'm seeing here is I total is equal to I5. So that's a great starting place. It gives us a piece of information right off the bat that we can use. I5 is going to be equal to I total, which will be 4.5 amps. Once you have I5, you can find V5. V equals IR. So V5 equals I5 times R5. You're going to do this several times throughout the problem. You'll find one variable and then you'll use V equals IR to solve for the related variable. So here we have 4.5 times 8 ohms, giving us 36 volts. Taking a look back up at our equations, now that we have V5, we know V total, we can use this first equation that we wrote in the loop theorem to get V4. So V total is equal to V5 plus V4. Therefore, V4 is equal to V total minus V5. Substitute in your value, and we get 18 volts for V4. Once we have V4, we can get I4. V equals IR, so I4 equals V4 over R4, giving us 1.5 amps for I4. It's a good idea to keep track of what you've already found within your equation so that you can easily fit these pieces of the puzzle together. Right now, if you look at this equation for I total equals I3 plus I4, we know all but one variable in there, so we can find I3. If we rearrange that equation, we get I3 equals I total minus I4, which gives us ultimately 3 amps for I3. Knowing I3, we can find V3, which would be 12 volts. Once we have that, you can see I've marked off the ones that we just recently found, V3 and I3, and that allows us to piece together another equation to use, and we can use that equation to find V1. We rearrange the equation for V1, make our substitutions, and we get 6 volts for V1. Knowing V1, we can find I1. I1 would be V1 over R1. And then we can see that we have V1, we have I1, and what we're down to at this point is finding, we know V3. We can see that V1 equals V2, and we'll be able to easily find I2. So this value for V1 of 6 volts is also equal to V2. For the final steps of this problem, we have a couple choices. Because we know V2, we can find I2 using Ohm's law. Or we can use either one of the first two equations found through the junction theorem. And it's nice to do that as a check. So we can see that I1 plus I2 is supposed to equal I3, which it does. 2 amps plus 1 amp equals 3 amps. Or we could do the same thing with the first equation and see that I5 equals I1 plus I2 plus I4, which it does as well. These problems can be somewhat involved, but if you start with the strategy of using the diagram and your junction and loop theorems to create a set of equations, it does simplify the process.